In this collection of videos, we are going to introduce a special type of series called alternating series. Now, up until this point, all of the series that we have been dealing with have been basically containing entirely positive terms. We've had a couple of experiences with negative terms where maybe the first couple of terms were negative, or maybe all of the terms were negative, and both of those were very manageable. So despite having this all the terms need to be positive requirement, these couple instances where all the terms were negative or the first handful of them were negative, those were things we could deal with by either factoring out the minus sign or just neglecting and ignoring those first couple of terms, which can be a little bit confusing. And even more confusing is, if that's how we're going to manage these negative terms, then why do we really even need to worry about negative terms at all? So the situation that we're really worried about in those other tests where we want to require that all of the terms be positive are series where that minus sign is really built in infinitely often, but not every single term. And the biggest example of this is what we would call an alternating series, where the series alternates between positive terms and negative terms, positive terms and negative terms, or vice versa, negative terms, positive terms, negative terms, positive terms. So every other term is negative in either way that you could imagine that. And those types of series are called alternating series. And up until this point, we really don't have any techniques for managing that type of series, and it's a series that comes up a lot in the type of work we're going to want to do a little later on. Luckily, we have a special test that is only usable for alternating series. It's a nice test, it's easy to use, and it's easy to know when you're going to use it because you only ever use it on alternating series. So that test is as follows. Let's suppose that we have a series where the a sub n's are alternating. So that is a condition that we have to check, even though it's not listed as one of these things right here. We truly must have an alternating series in order to apply this test. Then what we're going to want to do is think about what the series would look like without the alternating. So that's what the absolute value signs are for in both 1 and 2. Imagine what would happen if we didn't have that alternating behavior. If two conditions are true about what the terms would look like without that alternator, then we're going to be able to say that this series converges. And those two conditions are, if we throw away the alternator and look at the absolute value of the terms and take the limit as n approaches infinity of those terms and get 0, and if, when we throw away that alternator, the sequence that we're looking at is a decreasing sequence, if those two conditions are satisfied, then the sum of this series is going to be finite and we're going to have a convergent alternating series. Now it should be noted that the converse of the alternating series test is also true. If one of these conditions fails, then the series fails to converge and the series will in fact diverge. However, that's not built into the alternating series test because really, if the limit of these terms is not 0, or the absolute value of these terms is not decreasing, then we're looking at failing this nth term test, and there's going to be no way that those terms add up. So technically you could say that the series would diverge in that case by the nth term test for divergence. But I'm personally okay with viewing this alternating series test as sort of an if and only if. If these conditions happen, then the series converges. And if these things do not happen, if any one of these things does not happen, then the series diverges. Now we'll get practice with identifying alternating series. When they're written out in expanded form, it's very easy to identify an alternating series. However, when they're written entirely in this sigma notation, generally the tell that you have an alternating series is looking for something that's called an alternator. Something whose behavior, when you plug in different n values, is to just switch between +1, -1, +1, -1. So things like -1 to the nth power, -1 to the n plus first power, -1 to the n minus first power, those would all be alternators. And if ever your book is feeling kind of sassy, they'll use cosine of n pi as an alternator instead of one of these -1 to the n's of some sort. That's another version of an alternator. So that's one way that you could tell you have an alternating series if it's written in closed form instead of in expanded form. Now next I'd like to go through an example. I'd like to take a look at the series -1 to the n over n factorial, and I'd like to use the alternating series test to show that this series converges. Now the first thing that we need to do is show that this series truly is an alternating series. We could do that by looking at this alternator right here, but I think the best way to check if a series is alternating or not is to write out the first couple of terms in expanded form. When we do that, for this particular series, we get the example we saw in the first slide, which is -1 plus 1/2 minus 1/6 plus 1/24, and then so on and so forth. Part of the reason I'm a big believer in writing out the first few terms in expanded form is it gives you a feel for the series, and there's a little bit of a warning to be had in just seeing a -1 raised to some power and thinking that you have an alternator. For example, if I had -1 squared over n factorial, if you just got carried away and took any -1 raised to a power and said, oh look, an alternator, you'd be very wrong about -1 squared or -1 to the 2n. That's always going to be 1 and is in fact not an alternator. So I like writing out the terms to see the alternating happening for this particular check. Now the second check that we need to do is we need to look at the absolute value of the terms. That is, throw the alternator away. The absolute value of the thing that goes -1, 1, -1, 1 is just the number 1. And the n factorial part stays the same. So the absolute value of our terms is 1 over n factorial. If you think about what's happening as n goes to infinity, we keep making this denominator larger and larger. The numerator is just 1, so that limit is going to be 0, which is the first condition of the alternating series test after checking that we actually have an alternating series. And last but not least, we need to show that this absolute value of our terms is decreasing. And one of the ways that we can do that is to compare the value of the next term to the previous term. So when I take a look at what the next term would look like, what that's saying is let's take n plus 1 and plug that in everywhere we see an n. So that would be 1 over the quantity n plus 1 factorial. Now something we've seen before, but we could review if necessary, is that with factorials, n plus 1 factorial means take n plus 1 and multiply it by n, and multiply it by n minus 1, and n minus 2, all the way on down to 1. So one way we could write n plus 1 factorial is as n plus 1, kind of peeling off the first term, and then multiplied by n factorial. That's beneficial for us here because we can then break up this fraction as 1 over n plus 1 times 1 over n factorial, and 1 over n factorial is precisely equal to the absolute value of the a sub n's. So what this is showing us is that our n plus first term is a fraction, 1 over n plus 1, of our previous term, and that's going to show that our terms are decreasing. Another thing that was fairly apparent and obvious to us because we listed out the first couple terms of the series. So this is one way to formally show that your terms are decreasing. That's the second condition in the alternating series test. And because we have an alternating series, the limit of the absolute value of the terms is 0 as n is going towards infinity, and the absolute value of the terms are decreasing. Those are the three conditions for the alternating series test, and our series converges.